Hello, Ikra, can you hear me? Okay, fine, no problem. Okay, so we started basically talking about carboxylic acids and how they're soluble in water, and what's the difference between intramolecular hydrogen bonding and what's the difference between intermolecular hydrogen bonding. So if I just provide it, you know, just a small thing. So let's just provide a recap from from here. See, anything that wants to be soluble in water, it depends on the formation of hydrogen bonds. All right. As provided here, the smaller carboxylic acids dissolve in water in all proportions, but after this, the solubility rapidly reduces. Basically, they're trying to say as the chain increases, the solubility of carboxylic acids decreases. Now, why is that the case? See, for solubility to happen, what is required? We need to create hydrogen bonding with the water molecules, right? And we all know the two conditions for producing hydrogen bond is what? A higher electronegative element must be present compared to compared to hydrogen. So in this case, obviously it's oxygen. All right. No. So this is the first condition, and of course the second condition is that you know partial charges must be present. Okay. Now the thing that happens is that if I explain it, I explained it that day though. So if I just explain it here, so obviously this is a shorter chain, and we know that these groups are electron donating groups. So that means greater the alkyl groups, the greater the more electrons are being donated to this carbon right here. Now, what happens here is that the second condition is important here. What it is the second condition: partial charges and charges must be present. Suitable partial charges, to be exact, suitable partial charges should be present. Now, what happens is that you can clearly see that this one becomes partially positive and this one remains partially negative for hydrogen bonds to get produced. Now, the thing is, when the alkyl group chain increases, so here only one alkyl group is there, but this carbon is now receiving electrons from three alkyl groups. So obviously the what's it called, the negative charge here increases. Traditionally it is supposed to be partially positively charged, but due to the presence of these greater number of alkyl groups, this becomes negatively charged. All right. So since this becomes negatively charged, this one becomes positively charged because electrons move out from here to the bond basically. Now this, since this becomes positively charged, uh, the bond it can no longer attract the hydrogen in the water molecule. And you might wonder that why doesn't it attract oxygen? No, it's not possible. It does not have enough energy to do that. For hydrogen bonding to take place, the orientation has to be something like this or this. Okay. Now you cannot change the orientation. It's not that it's not that simple. So that is why since this one becomes positively charged, it can no longer attract the positively charged hydrogen bonding down here. I mean the positively charged, partially positively charged hydrogen atom from the water molecule. So as a result, what, no hydrogen bond is produced. Okay. Or the chance of producing, I think better I think the better term would be chance of hydrogen bonding creation decreases. So since the chance of hydrogen bonding creation decreases, solubility decreases. Okay, so did you guys understand the whole thing? Why the solubility decreases when the carbon chain increases? Ikra? Okay, I explained it to Rakshit though that day, so I think it's pretty simple. Now again, what do you call Rakshit? You tell me what type of hydrogen bonding is this? The bonding which is present between a water molecule and what is this? One, two, three, four. Butanoic acid. Tell me what is the bonding between a carboxylic acid? What do you call the hydrogen bonding which is produced between a water molecule and a carboxylic acid? Tell intra or inter? Intra, right? Is it? What does inter means? Between molecules. That means the molecules should will be same. Am I clear? Here are the molecules same? No. Two different molecules are being attached. So it should be intra. Did you understand? One minute. Okay, okay. Yeah, you're right. This is inter. Inter. So inter basically means that uh, opposite molecules or different molecules, if you say so. And again, there is another type of bonding which is present between molecules of the same type. For example, this one down here. So this is an example, as you can clearly see, the hydrogen bonding which is attaching two same ethanoic acid molecules. This is an example of what? Intramolecular hydrogen bonding. And that is of course which means same type of molecule. Okay, so I hope you understood. So that's how it goes. This is not that much important. Okay, now this is important. Strength of carboxylic acid. See, a little while ago we saw that alkyl groups are what? Electron releasing, right? So what are they doing? They're basically releasing electrons. So what happens? Increasing the chain length pushes electron density onto the COO. As I said a little while back, when you increase the chain length, what is happening? More number of alkyl groups are donating electrons to this group down here, the main functional group of carboxylic acid, right? So if the number of electrons increases in this region or this group, what is happening? The electron density is increasing, making it more negative and less stable. This makes the acid less strong. So more negative it becomes, the more, and basically in other words, if it becomes more negative, basically if the functional group becomes more negative, then the strength of the carboxylic acid decreases. Okay, now check this one here. For example, what if we introduce third party atom, for example a halogen like chlorine. Electronegative chlorine atoms withdraw electron density from the COO minus. Unlike the alkyl groups, okay, unlike the alkyl groups, they're electron withdrawing. Basically, they take in, okay, they do not give out, they take in. Opposite. So as a result, what happens? Again, the just the opposite takes place. Since it's electron withdrawing, it tends to absorb the electrons from this region, and as a result, this region becomes less negative and more stable. So the stability basically depends on how negative this functional group is. All right. So if it's less negative, it's more stable. So this makes the acid more stronger. So again, if it's more stable, then obviously the strength of the acid will increase. Remember, the strength is actually directly related to the stability of the carboxylic acid, and which is in turn related to the what group is present in the the whole structure. Did you understand? Hello. Okay, pretty cool. Again, the same thing. You can clearly see this one down here. Where is it? CO. This one. Okay. Now, what happens when you have this type of, when you have this structure basically? So in a dibasic acid, the second the second functional group withdraws electron density from the COO minus, making it less negative and more stable, and weakens the OH bond. This makes the acid more stronger. So what they're trying to say is that uh, now which one is second, it doesn't matter, it could be this or this. Okay, considering this is first and this is second, whichever is the second one of it basically is an electron withdrawing group. Okay, let's assume this is the electron withdrawing group, so it basically absorbs the electrons from this functional group. All right, and obviously it becomes less negative and it becomes more stable, and that is why the whole thing becomes more stronger, the acid. All right, so again, a dibasic acid is actually strong. I hope you understood why dibasic acids are strong. Dibasic acid is what? Dibasic acid is a type of acid which contains two functional groups of a carboxylic acid, or the same in the same structure. So you can see COOH, two identical COOH attached to the same structure, right? So that's how it goes. Okay, so this was just a introduction of theory. The real thing starts from here: the preparation of carboxylic acids. uh, I have showed this in the previous class. Do check out the recording, Ikra. No, basically I showed this in the last class. Again, I'm just providing a recap since it came here. So one way of producing carboxylic acid is obviously primary alcohols. So you can just directly oxidize primary alcohols and produce carboxylic acids. I have mentioned four types of oxidizing agents: potassium dichromate 6, and can Rakshit, can you mention the other three? I showed you that day, I mean yesterday, the three oxidizing agents name. Do you know them? Yeah, I mean it's there. I said the other three. Say. Yes, exactly. Acidified potassium manganate 7, right? Any two more, two, do you know? Phalanx. Sorry, what did you say? Very good. That's right. Tollens reagent. You are correct. So these are the four, along with dichromate 6, these are the four oxidizing agents which you should remember by heart, because these are the four oxidizing agents that you will encounter during your whole A2 course. Okay. And what is the reducing agent? You tell me, Rakshit. Since Ikra was not there last class, I'm pretty sure you might have forgotten. Uh, Rakshit, you tell me, what is the reducing agent that I have introduced? Maybe you have not checked the recording, that's why you have forgotten, right? It is lithium tetrahydroaluminate. And today I will provide the note. I have taken permission. Uh, I will be providing notes on a class-wise basis. So basically, up to how much I have taught you, I'll provide up to that much. Okay. So every day you will get a sheet. Okay, so I'm gonna provide you. I have taken, I guess, three classes so far. So yeah, I will provide the sheets of, including today. Today is the third class, so I will take what's it called? I'll provide three sheets today. Okay, and yeah, Ikra, if you want, you can write the notes during class, or otherwise you can just print it out. Am I okay? Is it okay for you? Okay, you can do it. Okay, so this is lithium tetrahydroaluminate reducing agent. Anyways, so one way of producing carboxylic acid is what? Direct oxidation of primary alcohol. See, you can see the reaction. One example: propanol being oxidized into propanoic acid, right? And this is known as, I mean, this is known as what? This is known as active oxygen. This is known as active oxygen, or it's also another one, nascent oxygen. Uh, Active oxygen is basically a very highly reactive form of oxygen atoms which comes out from oxidizing agent. Okay, the source of this active oxygen is the oxidizing agent. There is a reason why it's called oxidizing agent, because they can donate active oxygens. Only active oxygens can, oxidize, any of the substance present here. Okay, so the, what's it called, the presence of active oxygen is very important during oxidation, which can only come from oxidizing agents listed down here. Okay, and obviously potassium dichromate 6. By the way, dilute sulfuric acid is not a oxidizing agent. It acts as a what? It acts as a catalyst. Am I clear? Make sure to remember that. Now these were the reagents. Now condition is also very important. Use excess dichromate. Why do we use excess? So that, okay, now I'll tell you, to be honest, why use excess dichromate in heat under reflux? The main reason is pretty simple. For ensuring that the reaction goes into completion. Okay, so basically, in order to ensure that the reaction goes into completion, we tend to, we tend to basically perform this whole method during via heat under reflux, and we tend to use excess dichromate 6, so that some of it gets left even after the whole reaction gets completed, just to ensure that the whole reaction goes to completion. By the way, you guys know what's heat under reflux. We will discuss this back in unit 6, but I'm pretty sure you guys have heard about it and learned about it back in AS, right, Rakshit? Hmm. Okay, we have. So that's gone. Another way of producing carboxylic acid is, of course, you can clearly see. Oh, 1 minute. Let me just. Okay, so another way of basically producing uh, carboxylic acid is basically oxidation of aldehyde. All right, so you can also, okay, there is one way. What's it called? Yeah, that day I showed you guys in the last class. See, this was the part I showed in the last class. So you can directly oxidize primary alcohol to carboxylic acid. Okay, or you can also go from primary alcohol to aldehyde, then you can go to carboxylic acid. Now the question is, I mean, just for clarification, I would like to say that if you want to go from primary alcohol to aldehyde, you can use tollens. You should use tollens reagent or Fellings solution. If you use what's it called, potassium manganate 7 or potassium dichromate 6, there is high chance that aldehyde won't be produced. Directly carboxylic acid will be produced. The reason is pretty simple. If I talk about the strength of oxidizing agents, so I would say that, what's it called, potassium manganate 7 dichromate 6, sorry, and Fellings and tolerance. So this is the strength. Okay, as you go up, the strength increases. So the strongest is obviously manganate 7, and then it's potassium, what's it called, potassium dichromate 6, and obviously the weakest is tolerance reagent. So this is weakest, this is strongest. So if you use manganate 7 or dichromate 6, there is high chance that primary alcohol will be directly oxidized to carboxylic acid. But if you tend to use, if you want to get aldehyde first, then you can use any of these two weaker oxidizing agents, which are relatively weaker. Okay, so this will produce aldehyde. Now after you produce aldehyde, you can also, as they have showed here, there is, you can also go from aldehyde to carboxylic acid as well, and that is what they are showing here, that You can use again, you can from aldehyde, after you have used Tollens reagent, you can use another oxidizing agent, for example potassium dichromate 6, or any other oxidizing agent, whatever you want, in order to go from aldehyde to carboxylic acid. It's the same thing basically. This is like the full equation. uh, Most of the time this equation is provided in the question, but if it's not provided, then I would highly suggest to, they might tell you to write it down. So I will suggest you to remember the full equation. Just remember, actually just remember these parts. You don't have to remember this part or this part, just remember these. Okay, these are very important. These are very important because these are constant. These are constant for each and every reaction. The aldehydes might change, the carboxylic acid might change, but these will remain constant. All right, the byproducts and the reactants will remain constant. By the way, this is green in color. The reason why, and this is what, this is orange in color. All right, so we tend to see a color change from orange to green when this oxidation takes place. Did you understand? Okay. Now if I go for hydrolysis of nitriles, again the same thing. You can go from you can go from nitriles to carboxylic acid. The reagents used is obviously dilute hydrochloric acid, and obviously or sulfuric acid, whatever if you want, and obviously heat under reflux to make ensure that, look, why do we use heat under reflux? In a broad sense, without blinking your eye, you can just easily say, so that the reaction goes, to ensure that the reaction goes into completion. Okay, that's the main, or the main critical reason why we use heat under reflux. Anyways, this is the reaction. You can clearly see nitrile being added up. And so again, I'm saying again, these are constant. Am I clear? Make sure to remember these, and these will just change. Okay, basically just, the chain will change. So according to the chain, there is, the desired carboxylic acid will be produced. I think you can understand. So a 3 carbon chain nitrile will obviously produce propanoic acid, right? So that's how it goes. Okay, so these were the methods of production of carboxylic acid. Now there are some other reactions, you have to remember for carboxylic acid. One is of course the reduction of carboxylic acid to alcohol. It's just the opposite. We saw that yesterday, I guess. We saw it, the this one that, yeah, I showed. If you remember this chart, I'm telling to Ikra, I told it to Rakshit yesterday. If you remember this chart, I can assure you that you have remembered 70% of reactions related to alcohol, ketone, aldehyde, and carboxylic acid. Am I clear, Ikra? So try to remember this whole thing, everything basically. The oxidizing agents, reducing agents, this reversible thingy oxidized. If you can remember this in your brain, I would, I can say a lot of things have been memorized. So the same thing here, they're just provided in a professional format, nothing else. Again, you can clearly see that if you reduce, like we oxidized to get carboxylic acid, so if we just reduce it back, we'll get what? The same thing, right? We'll get the primary alcohol back, isn't it? In this case, we're going to use a reducing agent named lithium tetride to eliminate in dry ether. What is dry ether, sir? Ether is basically ethoxyethane, like the uh, ethoxyethane. What is the functional group of ether? This is the functional group of ether. Okay, so this is ethoxyethane. You can also give what's it called, uh, ethoxypropane. I mean, no, you don't have to, no need to go deep. Just want to let you know, dry ether is basically ethoxyethane, which is this compound down here. Ether is another functional group. I would like to clarify that ether is a functional group of something like this. Okay, this is an ether's functional group. Basically, it's in, a whole different homologous series. Just like carboxylic acid, alcohol, ketone, aldehyde, ether is also in homologous series, but it is not extensively discussed in your A2 syllabus. So I would not like to go that much deep. But for clarification, I just wanted to say that ether looks something like this. Okay. So this is ethoxyethane. The more specifically speaking, dry ether, which is used with lithium tetride to eliminate, it's basically ethoxyethane. Then again, if you want, you can, create another one. For example, CH3O, CH3, CH2. So this is what ethoxy propane. All right, so like this I think you can understand. You can create the homologous series of ether. Anyways, it's not that much important. Just remember this is dry ether. uh, Again, in room temperature pressure the condition should be remembered, and then I guess you can understand. This is known as active hydrogen. Remember the definitions we learned in IGCSE, or you guys have learned in IGCSE. What are the three definitions of reduction? Loss of oxygen, right? Exactly. Gain of hydrogen and loss of electron, right? Sorry, gain of electron, exactly. So yeah, the second definition is included down here, gain of hydrogen. And yeah, so that is why you can clearly see the active hydrogen comes in place. So remember this reaction. Actually, just remember this part and this part. The other things you can remember, or you can formulate by yourself, as per the question basically. Then again, we have salt formation reactions of carboxylic acid. So like carboxylic acids can form salts with metals, alkalis, and carbonates. Again, these are three mini reactions you have to remember. Just remember the bold letter general form. Okay, you don't have to remember these examples, because if you can remember the general format, you can easily formulate the main reactions basically. Okay, these were learned. You guys have seen this along many times in AS as well as IGCSE as well. Just a recap basically. Okay, look, A2 organic chemistry, if I sum it up, it's basically an amalgamation of AS organic chemistry with some 5% to 6% new stuffs. I have not even started the 5% to new percent new stuff. I will start it later. So whatever I'm teaching you guys right now, these are basically, I'm pretty sure you guys have seen these back in AS as well as in IGCSE at one point of time, isn't it? So it's nothing new basically. Everything is just, I'm just providing a recap basically and all the notes. So organic chemistry, it's kind of the same thing basically. All you have to do, my suggestion would be that the notes that I'm going to provide, obviously you're going to revise that. And the second thing that 80% students basically underestimate, that is, they think that by revising they might remember the reaction, but sometimes it becomes very much overwhelming. So I would suggest you guys to revise every day, or at least revise after 2 days, 2 days, by taking a 2-day gap. And after you revise, try to write it without seeing. So this kind of basically helps to impregnate the whole concept in your brain much more efficiently, compared to just revising or just skimming through the whole notes. All right, don't try to skim the notes. After you skim the notes, try to implement it, either by doing question paper or by writing the whole thing, writing the reactions by yourself without seeing. So that's going to be more efficient. So you will obviously forget if you do not revise like this. Am I clear? For at least for organic chemistry, am I clear, both of you? Okay. Oxidation of methanoic acid. Now remember one thing: carboxylic acids cannot be oxidized by using oxidizing agents, but methanoic acid is an exception. Okay, in the chart that day, as Rakshit has seen, and you guys have seen a little while back, in the chart you have seen that I have not, sorry, I have not expanded this part. Well, that's because normally you cannot oxidize carboxylic acid further, but methanoic acid is the only acid which is an exception, which you can oxidize further. Okay, so try to remember this, add them up in the chart when you write this chart down in your note. So it cannot be oxidized, but this can be done as the structure has effectively an aldehyde group. That's right, it does have, has an aldehyde group. You can clearly see that this part here is an example of an aldehyde group. So due to the presence of an aldehyde group, that is why, and we know a little while ago we saw that in the chart that aldehyde groups can be oxidized. Due to the presence of this aldehyde group in methanoic acid specifically, we can only oxidize methanoic acid further. To what? You can clearly see what? This basically forms carbonic acid, which can be used which can decompose to provide carbon dioxide. So you can just provide heat to it and carbon dioxide will be released. Okay, so if they tell you how to produce carbon dioxide, this is one way you can do it. Did you understand? Rakshay, hello. Okay. The next part is of course a reaction of carboxylic acid with phosphorus 5 chloride. Now, what is phosphorus 5 chloride? This is also popularly known as far as we know, this is also popularly known as test of alcohol. Okay, this is also known as test of alcohol. So we basically react it with carboxylic acid. When we react this with carboxylic acid, this is produced. Not actually test of alcohol. Sorry, it is known as test of carboxylic acid, but it also reacts with alcohols as well. Yeah, I will provide that reaction later. Okay, this is known as test of carboxylic acid or alcohol, whatever you say so. Anyways, so this is the reaction. You can clearly see PCl5 reacting with this thing down here, misty fume. This is the only visible observation that you will notice when this reaction takes place. Okay, so that's how it goes. So this is the, if they ask you in unit 6, most probably these type of questions come in unit 6. They might ask you identify the presence of the functional group COOH. So directly you can use this reaction and show that if misty fumes is produced, then obviously carboxylic acid functional group is there. Okay, so that's how it goes. Again, esterification, you guys have seen these back in AS as well. Again, carboxylic acid reacts with alcohol in the presence of a strong, I mean, how are esters produced? That's basically it. When a carboxylic acid and an alcohol joins together, again we know that ester is produced with water, right? And you can clearly see, look, this is an example, ethanoic acid and ethanol. So you can clearly see that, what is it called? So this OH part and this H goes away, and this OH and H reacts to produce water. Okay, and this ethyl part basically comes from this, and ethanoid comes from alcohol. Did you guys understand what I tried to say? The naming. Hello. Yeah. Okay. So these are pretty simple. The air stuff basically, nothing else. Uh, by the way, this H plus thingy that you see, this H plus thingy is coming from H2SO4 because dilute hydrochloric acid is used. Sorry, sulfuric acid is used as a catalyst. Nothing else. And esters have two parts. So the, again, as I said, the ethanoid. Sorry, I made a mistake. The ethanoid part comes from the carboxylic acid, and this one comes from the alcohol. Yes, it's written here. The bit ending in enoid comes from the carboxylic acid and includes the C in the carbon to carbonyl bond. The bit ending YL comes from the alcohol that is formed and is next to the single bonded oxygen. Okay, yeah, makes sense. So the bit basically which is ending in YL comes from alcohol, and the enoid thing part comes from the carboxylic acid. So if the, I think you can understand the naming. If it's propanoic acid, propanoic acid, and butanol, then I guess you can understand it's butyl propanoid, the ester, whatever it will be produced, right? Propanoid comes from this and this one comes from that. Okay, that's how it goes. Uses of esters, I don't think I have to explain that. Esters are sweet smelling compounds that can be used in perfumes and flavorings. Usually when you get to usually the commercial perfumes that you find in the supermarkets, these tend to use esters basically because they have pleasant smells. Esters tend to provide non-toxic pleasant smells, so that is why it's widely used in perfumes and food flavorings basically. Also, since basically they're soluble in solvent, so they can be basically found in liquid form. You can see some perfumes in liquid form, right? Instead of gas, I mean. perfumes, many perfumes, expensive perfumes, you can tend to see they're found in liquid form. Why? Because esters are soluble in solvents, basically water. Solvent here basically means water, so they're soluble in water as well. So the reason why they can be found in liquid form. And then there is obviously a mechanism to convert it into gas when you know pressurize the machine, the perfume basically. That is another thing. So that's how it goes. Again, you can also use it, what's it called, esters to in glues and printing inks. So because ester has, apart from having that, you know non-toxic pleasant smell, they also have this weird chemical property which allows them to act as glues, okay, or inks as well. Okay, so that's how it goes. Hydrolysis of ester. So hydrolysis of ester is what? Remember a little while back we saw this reaction, the reversible reaction. Is basically the backward reaction is hydrolysis and the forward reaction is esterification. I don't think there is that much to be explained. So basically you are adding water. What is hydrolysis? Lysis means breaking, right? And what is hydro? Using water to break down whatever the thing you want to break, right? So in this case you are wanting to break ester. So when you break ester, obviously the things from which it was produced, those will be produced, right? So obviously you can see alcohol and what? Carboxylic acid. That's right. Yeah, so that's how it goes. Again, there is another one. Instead of water, if you add sodium hydroxide and and perform this whole thing, you heat under reflux, then something else gets produced. What? Then basically a metal propanoid gets produced. I mean a metal alkanoid. If I provide the general term, metal alkanoid plus alcohol is produced when you add NaOH with an ester. Okay, so when you add an ester with an NaOH, you get a metal alkanoid. So maybe you can provide as uh, alkyl alkanoid. It's much more better. Alkyl alkanoid plus NaOH provides a metal alkanoid with whatever the alcohol which will be was present in the alkyl part. Sorry, in the, yeah, in the alkyl part. Okay, so that's how it goes. Okay, the next part, the another so carboxylic acid's derivative. So we were talking, what's it called? Uh, we were basically talking about derivatives of carboxylic acid. So ester is one derivative of carboxylic acid. What is derivative? Something which is produced from something else, right? So ester is basically a derivative. You cannot get it directly. You can get it from carboxylic acid. That's why it's known as derivatives. Another derivative that we get from carboxylic acid is obviously acyl chloride. Well, we saw a little while back how acyl chloride was produced, right? Do you see the acyl chloride produced here? So when you react PCl5, although this also acts as a carboxylic acid test, but this is also the method in which acyl chlorides are produced. When you react PCl5 with carboxylic acid, you get an acyl chloride down here. Okay, so this is one way. So what is acyl chloride? Acyl chloride is basically something which is the functional group COCl. Uh, it doesn't matter, the function, the chain increases. So in this case, since there are two carbon, obviously it's ethanol. If there are three, I mean if there are three, then obviously it's, we all know this is gonna be what? Propanoyl chloride. Oh, by the way, what's it called? This one down here, as you can see. Wait, what minute? Where is it? What is acyl? Okay, I'd like to say acyl is also referred as like this. Uh, COCl. This is actually acyl chloride. Okay, I mean this is the, we tend to say it acyl chloride, although the real name is methanol chloride. Okay, so remember word thing. The word acyl only goes with methanol. Okay, it's like a synonym of methanol. If you get to see two carbons or three carbons, then you cannot say it's an acyl chloride. It's a propanoyl or a whatever the number of carbons is. Okay, so if there are four, you can clearly understand it's going to be what? Butanoyl chloride. Did you understand? Ikra? Okay. So again, so this is how it goes. The Cl group is classed as a good living group. This makes acyl chlorides and acid much more reactive than carboxylic acid, acids and esters. So what they're trying to say is pretty simple. It's just that since it's an electron donating, what's it called? Since good living group in the sense that since this is more electronegative than carbon, so during any mechanism, this one when this bond breaks down, Cl easily gets out via the process called, we taught you in AS, heterolytic fission. Do you guys know what's heterolytic fission? Rakshit, do you know what's heterolytic fission? Hello, Rakshit. Do you know what's heterolytic fission? Wow. Ikra? Yes, breaking of covalent bond, but what is the difference? There are two types of fission process. Homo, sorry, what did you say? So you're trying to say, so this is how it happens, right? So in homolytic, what is produced? Very good. And water free radicals? Very good. And the bonded electrons are basically taken by, exactly. So I hope you understood what's the difference between homolytic. In other words, if I want to say, if I want to identify which bond will undergo homolytic or heterolytic, nonpolar bond undergo homolytic, polar bonds undergo heterolytic. So the conditions are pretty simple. I hope you understood. By the way, just want to let you know, free radicals are not produced in heterolytic fission. Here, what is produced? H plus, all right, and Cl minus. Am I clear? Because one guy is taking the electron. How come H plus will have the unpaired electrons, right? So remember that free radicals are only possible in the process of homolytic fission. Anyways, these are some fundamental stuff we saw. So so basically why it's called a good living group, because you can clearly understand Cl breaks down very easily via heterolytic fission, that's why. Okay, so that's gone. So then we have reaction with water, reaction with alcohol, reaction with ammonia, reaction with primary amine. These are the four types of reactions that you have to remember when it comes to acyl chloride by wholeheartedly. And I mean, why do you have to remember? Because of there is a very nice question they ask you in Unit 4 or sometimes in Unit 5 as well, which is known as organic synthesis. Organic means what? Compounds, all the compounds are organic, like any the compounds that you're going to work out are all organic, no inorganic. And synthesis means what? Basically the process. So they might ask you to basically produce a primary amine from a carboxylic acid. So what will you? So in that case, you might have to basically what? You might have to basically convert the carboxylic acid into an acyl chloride first, and then get your primary amine. Or it could be an ammonia. They might ask you to basically produce an ammonia, right? So that is why it is very essential that you get to remember each and every reaction as nicely as possible, because they might ask you anything to produce anything from anything. Like they might ask you to produce propanoic acid from, okay, produce ammonia from propanoic acid. So you can, one way is basically converting it first to acyl chloride and then producing this via this, by reacting with primary, what's it called, ammonia. Okay, sorry, this is primary amide. I made a mistake, sorry. Anyways, so that's why you should remember all the reactions. So with water we get to see the production of an carboxylic acid, See, so if you want to produce acyl chloride, I mean, if you want to produce, remember one thing, like if you want to produce carboxylic acid back from an acyl chloride, how did we produce acyl chloride? We produced acyl chloride via this process, right? But remember one thing, if you want to get propanoic acid, so what's it, this ethanoic acid back, the only way you can do it by reacting it with water. Okay, so if you react it with water, you will get the same ethanoic acid back. In that case, again, steamy white fumes of HCl are given off. With alcohol, though, if you react, you'll get a different thing. What? You'll get the reaction provides an ester. When you react acyl chloride with an alcohol, you get an ester. I mean, it kind of makes sense, doesn't it? Because the Cl part here goes away and the H part goes away. As a result, what happens? This O and this reacts. I mean, this part basically reacts with this this part down here, and this Cl goes away, and this Cl basically reacts with this H down here, which has come out from this alcohol to produce HCl. Did you understand why the ester is produced like this? Hmm? Yeah, exactly. Look, there is a note provided. This reaction is for making ester is much better than using carboxylic acid, as the reaction is much quicker and it is not a reversible reaction. That's right. Reversible reactions do not go to completion. As a result, there is a high chance that not all the esters will be produced or pure ester will be produced. That is why this if you react in acyl chloride with the alcohol, you will get your desired ester in a much more purer format. Okay, so that's what I wanted to say. Primary amide. I have talked about primary amide in the first class. I don't want to move on. What's a primary amide? I have provided a, you know, along with that, I have also provided what are primary amines, right? ICRA was there, isn't it? Remember, I talked about N-methylamide, amides and everything, isn't it? Tertiary, primary, secondary amides, right? Yeah, so I would suggest Rakshit to check out the class videos and try to get an understanding of what are primary amine, secondary amine, tertiary amine, what are amides, because these are very important. Anyways, here they're just showing the process of producing one, nothing else, from acyl chloride. Up to this much today. I won't go that much. Tomorrow I will start from polyesters, and a huge part has been completed. I can assure you 50 to 60% of organic chemistry in our ATU has been completed. Maybe more 2 classes and then organic will be over. Anyways, please, my suggestion is that contact with Shubhra sir and get those recordings right away. Am I clear? Especially Rakshit. Am I clear? Okay. And the notes, I am providing the notes up to how much I have taught as a PDF format right now on Messenger. Is it okay if I give you guys on Messenger? Okay, so I'm providing you in Messenger, and today's recording will also be sent to Shubhra sir. Tell him when he gives. Okay, that's it for today. Bye bye. See you.